Okay, so the next talk is about MultiFiT, efficient multilingual language model fine-tuning. This is presented by Julian.
Hello. So today I want to present MultiFiT, which is a method to pre-train language models that can be applied and fine-tuned for downstream tasks in a way that it's agnostic or that it works in multiple languages, but also it's robust and efficient enough to be used in a production application. This is joint work with people from the FastAI community, which I'm grateful to. And it was really a very good exercise and, in my opinion, successful of remote collaboration, because we actually never met in person. And our motivation is that we felt that there should exist a battle-tested benchmark method to perform NLP tasks in languages besides English. In this setup, we think we have a task in a language 1 and some corpus of annotated data in the same language, but also same thing in language 2 and many more. For datasets, we actually benchmarked and tried lots of datasets that the people in the community contributed. But to be able to compare to the other established methods, we chose to test. One is MLDoc, which is a more balanced version of the Reuters datasets. It's a classification task for news. It's in 8 languages. And then we also use CLS, which is product reviews from Amazon in 3 categories, and also 4 languages. So in both cases, the amount of data is kind of small by deep learning standards, which is good because we wanted to test how we would perform these low resource scenarios. So a word about related work. Current approaches for multilingual understanding will typically rely nowadays in either a shared vocabulary. So examples of these can be multilingual BERT, or also on parallel data across languages. That could be at the word level, sentence level, document level. So for word level, for instance, there's MUSE, which is this method to align word embeddings. But lately, there's many successful approaches that use both at the same time. An example of that would be XLM, which is a BERT-like pre-training task where you concatenate aligned sentences and mask some of the words. And also presented at this conference by Ardeche and Schwenk is LASER, which is a method that uses sec-to-sec architecture. And then as a byproduct, you obtain a fixed-length, language-agnostic representation for the sentence. And these methods are great. But of course, you need one of those 2 or both of those requirements. The shared vocabulary usually imposes a constraint that the languages have to be more or less close for this to work well. And the parallel data, of course, is other resource that you not always have at hand. And the other thing is that these methods are amazing in that you can do this zero-shot thing, where you train on one language and then can predict in a different language. But we argue that that's not necessarily important for most real-world applications. If you have to perform a task in some language, you generally have availability of some data. And sometimes only a little bit of data in your target language will be much more efficient than trying to do this zero-shot thing. And especially for some tasks, like disaster classification or hate speech detection, there's not perfect alignment between the labels that you will get in your target language versus the stuff that you have in some other high-resource source language like English. So our approach is training a single small language model for every one of those languages. And to make it more efficient, we use QRNNs, quasi-recurrent neural networks, which is a more small, efficient version of LSTMs, and also sentence Ps, so word tokenization. And we have 4 layers of QRNNs to train a language model. And then when we want to do some downstream task like classification, we pull the embeddings and have 2 fully connected layers. So one of the good things about this approach is that it uses 6 times less parameters than something like BERT-base, so the smallest BERT. And also, it trains really quickly. So you can train one of these language models on Wikipedia for the languages that we tested. in less than more or less 10 hours. Also, CPU inference is pretty fast, so you can use this in production without much problem, which we think is very important for applications. Some experimental results. In this case, we're using MLDoc and training only on 1,000 samples in the target language. So it's the fully supervised use case, right? So the top column, we have laser. Then, so laser gives us this fixed embedding for the sentence, so we can train a linear lay on top of that. Then we're also benchmarking against multilingual BERT, and for Chinese and German, we actually had access to a monolingual BERT that is trained. And then we tried MultiFiT, which is our method, in 2 versions. So one pre-training in Wikipedia, and in the other one, we didn't do Wikipedia pre-training, but we did use the documents that we had, the news articles, to do pre-training. So as you can see, the results are a little better across the board and sometimes a lot better. But what happens with zero shot? So in some cases, you may actually do care about zero shot. So we wanted to see how we could combine the best of both worlds. So zero shot, let's say that we have a model like laser that allows us to train a model in the source language. So we can, after we have that method, we can apply some distillation kind of idea. So we can use this laser model to predict on my target documents in the train set, right? And on the other side, we have the language model in the target language that we are pre-training, let's say on Wikipedia or some large corpus. We can also fine-tune it, the language modeling, for my target documents in the target language. And then we can combine the two. We can distill the labels that we obtained from the laser-based classifier to our language model. And that gives us very good results. Because the labels that we obtain from laser or other cross-lingual methods are kind of noisy, and the language model in the target language acts as a regularizer. So as we can see again, we get good results for all the languages that we tested. In some cases, like Chinese and German, the results are quite impressive, and actually Russian is a little worse. So we wanted to see why this could happen, and we analyzed that our models were actually, the language models was actually made the classification task more resilient to noise. To test that, we added artificial noise, so we corrupted some of the labels. And so here in the x-axis, we see the number, the percentage of noise that we're introducing. And in the y-axis is the accuracy that we're obtaining. So the blue lines are 2 different training sizes of our language model pre-training. And as you can see, up to 30 or 35% of the corruption, the performance doesn't get affected by much. But if you don't do that, the performance drops by a lot when you're adding this corruption. So the takeaways are that a small amount of target language data goes a long way. So even if it's 100 examples, you should try to annotate a little bit in your target language, and that will give you great performance, much more than trying to transfer across languages. Also, language model and cross-lingual representations are complementary, so you can get the best of both approaches. Monolingual models still win when it comes to speed and resource efficiency, so if you want to put your model in production. And we released the code and all the pre-trained models, so we invite you to check out the code and add more languages if you want to. Thank you so much. I'll take questions.
Thank you very much. I think we have 3 minutes for question and so any comments? Okay, so I have a question. So do you have analysis what kind of representations learned by your model?
Right. So we haven't done that analysis. We could extract a representation based on the poolings that you do over all the token embeddings that you could apply to different tasks. So that's future work.
Okay.
Yes, hello. Sorry, maybe I missed that part, but how did you zero-shot your monolingual language models to other languages?
Right. So it's a distillation kind of process. So you are using some other cross-lingual models like laser. So you can train laser on the source training data, and then use that to get predictions for your target training data. So you are bootstrapping from Laser, but then you combine it with a language model, and that actually gives you much better results than just using a zero-shot method.
Any further comments, questions? I have another one. Do you have any ablation studies to measure that to isolate whether the gain comes from?
Yeah, so there's a bunch of those in the paper. Let me think. So, I mean, there's a lot of gain coming from the subword tokenization. If we tried different tokenization strategies, and that made it very different, specifically for languages that are very morphologically rich. That's one thing I can say.
Okay. So if not, so we will thank our speaker again.